Thank you. So yeah, as I was saying, I'm not an expert in hyperspectral image analysis. I'm a simple bedrock geologist who worked in mineral exploration before that. But I found myself in possession of a lot of hyperspectral data, and I decided to see what I could do with it. And this presentation is the result of my playing around with the data, talking to people, reading papers, and trying to grow hyperspectral as a technique in Ireland and elsewhere. So thank you all for joining me this afternoon. The title of the talk is Hyperspectral Image Analysis and the Geological Survey of Ireland. And I'm going to show you the last slide first. This is because I'm a geologist and I'm about to show you quite a lot of equations and graphs. So I just want this nice interpretable fence diagram of 4 drill holes to stay in your mind and remind you that this is about geology and we will get there. So the talk is going to cover what is hyperspectral imaging and a very brief overview of some of the existing applications. And then I'm going to talk about the GSI's core scanning data, how we get the data, the corrections that go into the data, a little bit about understanding and using the data. And then I'm going to show you a case study of a project that we worked on in Geological Survey. So first of all, what is hyperspectral data? So I'm going to give you some basic definitions, which I'm sure some of you will be aware of. Visible light imaging is the standard image that you take with a normal camera that everybody has on their phone. These images sample 3 bands of the visible portion of the electromagnetic spectrum, red, green, and blue. If I refer to this throughout the rest of the presentation, I'll just be referring to them as RGB images, and that will just mean standard normal camera images. Then spectral imaging is broadly divided into 2 disciplines, hyperspectral and multispectral. And these images cover more of the electromagnetic spectrum than just the visible, and they also sample more than 3 bands. A rough definition is multispectral images capture 3 to 15 bands, and hyperspectral images will capture hundreds of bands across the electromagnetic spectrum, appearing almost continuous. So here's the electromagnetic spectrum. I'm sure most of you have seen this. And I'm going to be talking today. Is my cursor visible if I use it as a pointer?
Yes, it is.
Thank you. So we're looking at the visible. That will be the RGB images, the shortwave infrared and the medium wave infrared. These are often referred to as SWIR and MWIR. I'm going to be talking about these because those are the cameras that we have. So just an overview of what the image is. Both hyperspectral and multispectral, they're best off being thought of as 3-dimensional images, where your typical X and Y, that would be your flat image that you take with a normal camera, but the 3rd dimension will be wavelength, and you can plot this 3rd dimension pixel by pixel and look at a spectrum, or in multispectral image, it will be a more sparse spectrum. And the spectral resolution is determined by the number of bands that your instrument is capable of sampling. And the more bands and the closer together they are, the bandwidth will give you a higher spectral resolution. So some applications of hyperspectral imaging. So Christine referred to it as a new and developing technique, and that's certainly true for geology, but in remote sensing, it's been used for quite a long time. And a lot of the algorithms and techniques that we use in hyperspectral and geology come out of other fields, particularly remote sensing. Satellite, airborne, and drone-borne hyperspectral cameras were some of the first developed, and it's quite a mature field in remote sensing. The ability to handle and work with the data is quite well established. It's also used quite extensively in food safety and in recycling, and it's becoming more applicable in environmental monitoring. So just a quick whistle-stop tour. It's often used in land use in remote sensing. The normalized difference vegetation index is a well-established technique. I'm putting that in there to show the maturity of the technology in remote sensing fields, that there are just standard tests that are automated and applied. Again, in crop health, there are many different applications depending on the type of crop and the type of acquisition you have available, but it can be used to diagnose health and identity issues of crops. It's used in food safety. As you can see here, there are contaminants in the seals of this product that aren't visible. You can only see them in the infrared, and you can map out the moisture content of bread to see are things going stale. It's also being used in recycling, and particularly the medium wave data is a growing application in recycling because it can distinguish black plastics, which is otherwise a significant problem. But you can see here you have the RGB image at the top, and at the bottom you can see that it's very easy to distinguish between these white plastics with a hyperspectral image. And it's also used in environmental monitoring. As I mentioned, you can map quality in water bodies. And here there was an application where they could actually quantify the amount of oil present in seawater following an oil slick. And finally, quality control in pharmaceuticals. This is an image from a manufacturer, Specim. They've switched a paracetamol pill with an aspirin pill, and the hyperspectral can just immediately tell which is which with very straightforward coding. So that's where we're coming from, what the geological hyperspectral community is taking and developing and trying to put into our own work. So now I'm going to talk about what we're doing at the Geological Survey of Ireland. So we are acquiring hyperspectral images. This is our core scanning setup. You can see this is the table, and it can hold a 1.5 meter core box. This is a Specim Sisu rock system. Specim is a hyperspectral camera manufacturer, and inside we have 3 Specim cameras. We've scanned over 1,400 drill holes. They vary in length from 10 meters to a kilometer, and that's led to about 80 terabytes of data. And we fully intend to scan our entire core collection, which is about 500 kilometers of core, and the GSI is drilling ourselves. So we're probably adding 3 or 4 kilometers of core a year to our collection. We're going to be scanning all of it. We're also beginning collaborations with industry where they will give us their core to scan. So we're not scanning just our own holdings. We're basically scanning anything anybody sends to us. So this is going to be a very significant data set that's going to be public and free, and is currently public and free. So this is the inside of the system. These are the 3 cameras: an RGB camera, a medium wave camera, and a shortwave camera. And this table passes under each camera, and each camera collects its image, and the table comes back out. And that takes about 60 seconds. So to acquire a box of core will take 60 seconds. To acquire an entire hole of core will take about a day, give or take, depending on the length of the hole. So it's a rapid, high data density process. And just I was mentioning the spectral resolution earlier when talking about hyperspectral cameras. So our medium wave camera covers it covers from 2,700 to 5,000 nanometers, but it does it in 154 bands. Whereas our shortwave camera covers a much shorter wavelength range, but it does it in 288 bands. So the spectral resolution on our shortwave camera is much higher than the spectral resolution on our medium wave camera. And our RGB camera obviously captures just 3 bands because it's traditional imaging. So what do you get out of the machine? What you get is 9 files per camera. So that's 27 files for a box, and they come out in a file format called MV, which is stored as band interleaved by line. And it's about 1.5 gigabytes per box. And if you think most holes around 600 meters would be 100, 150 boxes. So we're definitely talking about big data. We're in the big data domain. And this is what it looks like in your output. You get an MV header file, and you get a .raw file, which is a binary file band interleaved by line. And the header file tells you tells the computer how to interpret the binary file. So this is what the raw data looks like in an image. This is uncorrected. You can see they're slightly different fields of view. They're quite fuzzy. There's different spatial resolutions for each one. And as you can see here, it's 384 pixels across for the shortwave, which works out to about 1 millimeter pixel sizes, depending on where the focus point is. And then 4,096 pixels for the RGB and 640 for the medium wave. So 640 for the medium wave works out at about 0.5 millimeter per pixel, and 4,096 pixels for the RGB works out at very high resolution geological imaging, core imaging. So this is what you get out of the camera. But in order to do any work with it, you need to do some corrections and processing. And this is where the graphs and equations are going to come in. This is what the process data looks like. You can see it's much brighter. These, by the way, are false color images. So almost arbitrarily have assigned 3 bands to red, green, and blue to display as an image. So you're only seeing here 3 bands of the hundreds available. And once they've been corrected, you can see the images are much brighter and sharper and something you can look at and begin to get something out of. So how do we go from this to this? I'm going to show you on a single pixel. So circled in red is a pixel of a calcite vein that will be used for the following examples of how we do the data correction. And I should mention there are a number of different ways to do the data correction. That's one of the most intimidating things about hyperspectral data, is every step of every process has multiple different ways of doing it. So what I'm showing here is the pipeline we've used in Geological Survey Ireland, which may or may not be the best, but it works for us. So at the top is a raw pixel. So this will be directly from the MV file, 1 pixel in the calcite vein. You can see it has this shape and it's quite noisy. This here is a pixel of the dark reference. The dark reference is an image captured by the camera with the lens cap closed. So there's no light in this image at all. All you're capturing is the electronic noise that the camera makes itself. And then this pixel here is a white reference. Again, you can see it's quite noisy. You can see the influence of the dark reference on the data from the white and the data spectrum. And this white reference is an image of a material that's known to be 99.9% reflective in the short wavelength range. So in this case, it's a material called Spectralon. For the medium wave, we actually use aluminium as the white reference. And we just simply do a flat field correction, which is the data minus the dark reference to remove this noise, then the white reference minus the dark reference, again to remove the noise. Then we divide the data by the white and times it by 100, and that gives us values in reflectance. We do the same process for the medium wave. You can see, because of the lower spectral resolution, that it looks significantly different. The noise is more dispersed. There's just less bands to worry about. And you can see there's this strange effect going on in the aluminium, which is removed from the raw spectrum, and you get the corrected spectrum. Exactly the same process, dark and white. And we do a similar process for the RGB images because they're captured in the same way and presented to us in these NV files. So here you can see the process of this is a calcite pixel. You've got this raw spectrum, which is noisy and has this curve because that's the way the camera collects the reflectance. Once it's corrected, you can see that there is still some noise in there. And so we smooth it out. Again, there are many, many, many ways to smooth the spectrum. We just use a Savitsky-Golay filter. It's computationally quick and it does the job, but there are pros and cons to every filter, and every step is a research project in itself with working with this data. So sometimes you just pick away and be consistent, and what I have found. And again, you can see the same process for the medium wave. You can see the medium wave is less noisy. You have a few bits at either end of the camera, but in general, it's less noisy. This is because of the wider bandwidths. It has less spectral resolution. But we do a bit of smoothing on the medium wave as well. And then the final step in the pre-processing or correction is we calculate the convex hull, or we remove the continuum. So here at the top, you can see the smooth corrected spectrum that you'll be working with. Then you calculate the convex hull and you divide the data by the convex hull. The advantages to doing this are that all values are now between 0 and 1, which means you can compare spectrum much easier. And these absorption troughs, which are very important as you see going forward, are more easily identifiable. They become more prominent. So it's just a standard practice to perform the convex hull quotient for many of the processes. So the next step is masking. And again, there are many, many, many methods of masking the image. And by masking, I mean extracting the non-geological material from the image so that you aren't including it in the calculations you'll do later. And luckily for us, almost all of our core is stored in wooden core boxes, and wood has a distinctive spectral response in both shortwave and medium wave. I've got here the spectras of a wooden core box. So we can do a simple Pearson correlation pixel by pixel to identify the core box, and you can see here, and that we can then extract that from the image because we know where the non-geological material is, and this would be the result. However, having said we use Pearson correlations, we actually don't, because the Pearson correlation is performed pixel by pixel and it works best on continuum removed spectra. So both performing the correlation and removing the continuum have to be done on every pixel iteratively to some extent. So it's best to do that in terms of computation and time on as fewer pixels as possible. So we've developed some trained machine learning models. This YOLO V6 model was developed by a research team in China using our data, and it can identify the core box from the table and remove it. So you then don't have to work with pixels that aren't in the core box. This actually works with all three formats. This model works with RGB, shortwave, and medium wave data. And actually, we managed to provide them some hyperspectral imaging from the Swedish Geological Survey, who have metal and plastic core boxes in their collection. So this model works on metal and plastic core boxes as well as wooden. And then in GSI, we trained a multi-layer perceptron model using Pearson correlation as the ground truth data so that we could perform masking on uncorrected data, which just speeds up the process a lot. And all of these models will be available from GSI. These MLP models, we made them in-house and can share them anytime. But the YOLO V6 model, the Chinese team want to wait until they've published their paper before they'll let us publish the model. But they will all be available, and we'll be soon posting them on our GitHub. So despite all of that, pre-processing is actually very quick and automatable because it's done in code. All of the code to do all of the steps I've spoken of here is available from the GSI. We'll soon be putting it up on our GitHub. And it uses open source Python libraries. So all the data is available for free. This spectral Python is actually from the remote sensing community. And Highlight is from the Helmholtz Institute. And they've designed it to work with all kinds of data. It works with drones, tripod mounted cameras, core scanners. But they've just completed a big core scanning project themselves. So it's becoming more tailored to that. And again, it's freely available. There's also commercial software available for working with hyperspectral data, but I don't know too much about it because I couldn't get a license. So once you've acquired your data with the spectral cameras, you've been through all the pre-processing, you've made all the decisions that you need to make to get an interpretable image, what do you do with it? So we know that energy of different wavelengths is absorbed or reflected by the material you image. And the absorption or reflectance can vary with mineralogy or mineral chemistry. So I've just got here some common minerals. These are taken from the USGS spectral library. And I'm just showing the wavelength ranges that are available on the GSI camera. And you can see that they're quite distinctive. So you can, by looking at a corrected interpretable spectra, begin to make some decisions as to what the mineral might be. And you can look at these individual features and map the minimum point of them. And this is the main tool that I'll be showing you in the case study. So here is a calcite pixel, and I've used the tool from the Highlight library to identify the 5 deepest features. And as you can see, there are 4 main ones and then a debatable one. And this is because, as you'd expect, the 1 millimeter pixel in this calcite vein is going to be calcite. There's not going to be too many other minerals having an influence on it. The features are very clear, the spectrum is not too noisy. However, when you look outside of a calcite vein into a piece of fine-grained carboniferous limestone, you have much noisier spectra because it's darker overall. Each 1 millimeter pixel will be influenced by a number of minerals because this is very fine-grained material. However, you can still see the calcite, the carbonate wavelength here, and you can pick out other features. And this aspect is what we used in our case study. And I'm just showing here, we're going to look at 2 main features. This is an excellent publication which lists as many geological, mineralogical features in hyperspectral data. And I'm highlighting the diop sheet silicate feature. So this will be clays and mud minerals at 2200. and the 2320 carbonate feature. So the case study I'm going to talk about is a project myself and a colleague of mine, Marcus, did on the Carboniferous of Ireland. And as Christine said at the very beginning, hyperspectral is becoming more and more used in geology for identifying alteration around mineral deposits. But we felt as a geological survey, we should maybe look at lithological tools, because it's not really something that exploration companies are gonna fund unless they've got a direct need. But it's something we felt geological surveys should be looking at for applications for this. So lithofacies discrimination through spectral facies. So why did we choose lithofacies discrimination? This presentation was altered from something I gave to non-geologists. That's why I define facies for you. But stratigraphy is derived from a combination of rocks that share a lithofacies and a similar age. And we have 500 kilometers of core, which have varying qualities of lithological log, from excellent, that were done with really detailed micropaleontology by experts who knew exactly what they were looking at and give you a log with a lot of confidence, all the way down to no log at all. So we needed some kind of objective technique to quickly and consistently compare these, because you might have a log that was done on a Friday afternoon by a very fresh graduate versus a log that took 6 weeks of a very experienced geologist to do, and they're not really comparable, or you have to put some work in to make them comparable. Whereas if you've got an objective framework to hang that data on, it will make it easier to apply definitions across varying data sets. And again, I don't think I need to tell you guys why having improved stratigraphy and improved maps is good for everybody. So the case study, lithofacies discrimination. An alternative title is monotonous grey rocks, which I think is the most clear definition of the Irish Carboniferous you can get. So I'm going to be talking about a hole that the Geological Survey drilled in 2016 in County Roscommon. So this is an area of the Carboniferous stratigraphy that wasn't particularly well understood till this project that was done in 2016. It's an area that should have some mineral potential, but it hasn't really been explored because of the lack of understanding in there. But it's generally Visayan limestones, and they are visually very difficult to distinguish. You need an experienced eye to really log well in this area. But we have a very reliable lithological log from a very experienced geologist who has a very trained eye for the Carboniferous in Ireland, and it has detailed micropaleontology and thin section analysis. So these were logged by my colleague Marcus, who's been working in the Carboniferous in Ireland for a very long time and has seen an awful lot of it. And we just built a very simple decision tree using the two spectral features that I mentioned earlier. So we took our denoised hole corrected spectrum, we used the feature finding algorithm, and just identified what features were present. If there was the 2200 nanometer feature present, which is related to sheet silicates, then we could say, okay, there's something other than just carbonate in there. So it's a muddy carbonate rock. If the 2320 feature is present, then it's a carbonate, and we can build up these three facies: clean carbonate, muddy carbonate, and non-calcareous. So that again is just something you can very quickly do and is of some use. But we wanted to go a bit further. So we looked in the literature, and it's well known that the wavelength position of the carbonate feature varies with the chemistry of the carbonate you're looking at. The wavelength becomes shorter if you have magnesium in the as the cation, which means you can distinguish between calcite and dolomite. Now, a small caveat here is the wavelength feature also becomes shorter if you have iron in there as well, and you need another camera to be able to distinguish iron carbonates from magnesium carbonates. But we felt confident that there's an awful lot of dolomite that we know about in the Irish Carboniferous, so we felt comfortable saying we were detecting a change from calcite to dolomite, which meant we could. Okay, so first of all, let's talk about the minimum wavelength position. On the left is the continuum removed spectra at the top, and on the left is simply plotting the continuum removed spectra in the region we were interested in, so from about 2290 to 2350. And you can see that the curves are slightly different in each. This one here, we performed the continuum removal only in this area, which is why you reach 1 on both ends of it. So the curves are drawn slightly differently, but the minimum wavelength position is always the same. It's 2335.06. And that is because that's the band center. So even though it looks like you're working with continuous data, you are actually working with discrete data. So you need to be able to find where the minimum point is within the bandwidth, because it's unlikely that this minimum position is in reality exactly on the band center. There are a number of different ways to do this, as with everything when you work with hyperspectral data. And we decided to use the simple quadratic method. So there are other methods available. There's other polynomial methods, and there's a Gaussian fitting method, which implementations for these are available in the highlight library. But we decided to go with the simple quadratic method because it's computationally the quickest. And they allow us to determine the minimum wavelength position within the bandwidth and not just give the minimum bandwidth as the center. So if you take these 3 points, depending on how you draw the curve, the lower point could be anywhere between here and here, or anyone between here and here. And as you can see, when you use the simple quadratic method sorry, there's a lot of chat coming up that's distracting me. I'll try and get to all of it at the end. When you look at it on the non-extracted feature, you can see you have a shorter wavelength than on the extracted feature, and none of them are perfectly within the bandwidth. I recently had an argument that you shouldn't use this local hole removal extracted carbonate, but at the time we did this case study, that was what we'd come across in the literature. So that was the methodology we applied, and we applied it consistently to every pixel in every box throughout the hole. So the results are comparable, even if it's perhaps not the best method. And here is a map of the minimum carbonate feature, the minimum position. And you can see there are variations in the position of the absorption feature. You can start to see these veins have a slightly different, perhaps mineral chemistry to the carbonate in the sedimentary mud stain. Black pixels are the mask, and there are also pixels that you can't find, the 2300. So this is of some use, but I mean, it's not terribly exciting. But if you look at the entire hole, you can see that there is actually significant variation in the carbonate position, as well as regions where the carbonate is absent. So on the left is the log from Marcus Pracht, which has these formation boundaries tied in. These formation boundaries are determined by detailed micropaleontology. We have as much confidence as you can have in them. And you can see there's variations within the formation. So the Oakport limestone is beginning to look a bit more dolomitic in its base. And then the Kilbride limestone seems to have large parts where the carbonate feature is not present. The same with the Woolsoshen and the same with the Ballystine. Now, anybody who's worked in the Irish Carboniferous, if you told them that the Kilbride limestone and the Ballystine formation are not carbonaceous, they'd laugh at you. Everybody knows that these are limestones. So yeah, this was wrong. We didn't understand why. But putting that aside, we could now define 8 spectral facies and attribute each pixel based on our decision tree classifier. So first of all, is it muddy or clean limestone? And then is it calcite, dolomite, dolomitic calcite, calcitic dolomite? And we could define these just using 2 features. And as you can see here, it looks quite interesting. You can see that the veins are showing as very clean. Most of the limestone most of the rest of the box is clearly calcitic limestone, but quite muddy, this green color. A few places you have the odd pixel that are a bit more dolomitic. But in general, you can start to see something. But there are a lot of these gray areas, and these are non-carbonaceous, apparently. So we didn't believe this. I actually went to the core store after I saw this, and I put acid on these sections, and it fizzed. We looked at them under thin section and knew that they were carbonaceous. So we needed to find an explanation as to why the 2320 feature was absent. Just to clarify, when I say the feature was absent, that means that the feature wasn't one of the 5 deepest features identified by the highlight library. So the feature may be present, it just wasn't registering, it wasn't significant. So then I found this paper written in 95 by Van der Meer. I don't have the reference up here, but it is at the end. And what they did is they took chalk and slowly added graphite to it. And this showed as the proportion of graphite was added to the chalk, the carbonate feature slowly flattened out. And we thought, okay, we're maybe seeing organic material in the limestones, which we know is present. And once it reaches a sufficient quantity, then we're not seeing the carbonate feature. So what we don't have is, we don't have non-carbonaceous rocks. We have organics quenching the carbonate feature. So we began to use this as a proxy for organic material, obviously with some caution, because there might be a tough band which is going to show as non-carbonaceous. There are sandstones in thin bands, things like that, but we thought this would be a relatively useful proxy. So we completed our decision tree. We had a quenched carbonate facies and we had a quenched carbonate facies with siliciclastics. So we could define 10 facies in monotonous grey limestone. And this is the result. And you can see that even within formations that are well defined, you can see where you go from a muddier limestone up into a much cleaner limestone with some thin dolomitic bands. You can see this large area of limestone. And actually what we recognized was that where you get more and more of the quenched facies, this point here is actually the Visaean-Tournaisian boundary. So we can see that there was a significant change in the amount of organic material contributing to the rocks as you went from the Tournaisian to the Visaean. And you can see that you could almost, if you were to just draw boundaries based on the hyperspectral, a lot of them would match with the micropaleontological boundaries. So we thought, okay, this was quite useful. But how much do we believe it? There were 34 thin sections collected from this hole. 24 were collected back in 2016 before this project was thought of. And these are biased towards the cleanest limestone in order to have the fossils for the best age estimate. But we collected an additional 10 for this. And I had Marcus go through the thin sections and try to predict which of these 10 facies he thought the thin section would fall into based on, can he see dolomite in there? Can he see a lot of organics in the thin section? How much siliciclastic material can he see? And this is sort of explains why this might not work perfectly. You can see this is an area where the thin section was taken from, but we don't know exactly which part of this is the thin section view he was looking at. So there is a definite problem in scale. If the thin section was taken here, then Marcus is going to predict clean calcite. If it was taken here, he's going to predict it's more dolomitic, and the same here. But what was also interesting about this is a lot of the dolomite that's only visible in thin section is very clear in the hyperspectral image, which is quite a useful tool in itself. And if you were to look at this, you would consider it a relatively clean limestone. But actually, when you look in the hyperspectral, it's quite a dolomitic, muddy limestone. So it's giving you more information than the naked eye can, and the thin sections give you some confidence. So we were pretty good at predicting which facies it would fall into based on the thin section description. It was difficult to the most failures were on the quenched facies, and that would be because maybe the organics weren't in the particular field of view he had. That's one explanation. Another explanation is that organic presence is only one factor contributing to the quenching of the carbonate feature. But this gave us quite a lot of confidence that what we were seeing in the hyperspectral was related to the lithology, and these lithofacies were these spectral facies were useful. So we applied it to 3 more holes in the same area to see if we could draw some correlations. And now we get to the first slide I showed you. You can see these Spence diagrams. So the black tie lines are correlations based on stratigraphy, based on detailed micropaleontology. And what I find really interesting is you can see facies changes in limestones of the same age. So if you look at the Oakport limestone, it's always clean at the top. However, the thickness of the clean limestone you have decreases towards the west, and you get muddy limestone earlier. And again, you start to see these bands of mud. So this is referencing changes in the environment over time, difference in the carbonate fascies. And again, you see this dolomite at the base of the Oakport limestone. However, over here, you see it's actually lower in the Kilbride limestone. So either these are two different dolomitic events, or the one dolomitic event was later than all of this. So there's lots of information it gives you that you can interpret and leads to good follow-ups, which I think is why, and it's objective. Yeah, if two different people logged these holes and had these formations slightly differently, the spectral features would be the same. And you could look at, okay, so there is a boundary here. He's put it a bit lower on his log. Maybe we could think about moving it. So it's going to be quite a useful tool for comparing data sets of different ages, which is something everyone in the Geological Survey has to do on a regular basis and finds quite difficult. So yeah, we believe we've demonstrated that there's a wealth of geologically valuable information contained in hyperspectral core scans. It's just extracting and interpreting the information from the data is the challenge. The data gives you an awful lot of information. It's deciding what to ask of it. It will only give you what you get out, and if you ask it the wrong questions, it will give you nothing. But there's a large scope for research in this field, and there's free software. Geological Survey Ireland are making a huge data set freely available. The Norwegian Geological Survey have a large data set. The Swedish Geological Survey have a large data set. And we did this entire project using only 2 features. There are a lot more features that can be used, as well as machine learning techniques, other spectral techniques that you can apply to it. We just used a small part of one technique, feature extractions. There's a lot more that can be done from this. So what are we doing now? What are we going to do in the future? We need to look at the medium wave data. First of all, spectral quenching in the carbonates doesn't affect medium wave data. So that's something we're thinking about and looking how to apply. The medium wave data can also determine tectosilicates, quartz. So that's something we can think about, the quartz distribution in our holes. And perhaps we could even go back to the 2200 feature. And rather than just using a presence or absence metric, we can start to say what clay mineral is in there and begin to look at what was contributing to the sedimentation at the time. So that's projects we're looking at starting. We also have a new / ongoing project. We've partnered with the National Museum of Ireland to scan their mineral collection. They have 20,000 well-characterized, well-documented mineral specimens, and we're going to try and produce a spectral library from those mineral specimens on our 2 cameras. This will be one of the largest MWIR libraries publicly available, and it will be a very significant SWIR library. And it will all be collected on the same instrument. So there are quite a number of spectral libraries out there, but they were all collected on various different instruments, various different times, things like that. So this will be one consistent library, which I think will be a very useful resource for research, particularly machine learning. So the next steps for hyperspectral in Ireland and beyond. So GSI, we funded a postdoc project with the UCD School of Food and Biotechnology. So UCD's University College Dublin, they have a hyperspectral expertise centre focused around food safety. And we decided to leverage their hyperspectral expertise and add the geology. And we're funding a 2-year postdoc project. And they are looking at some of our core with machine learning methods to try and predict some petrophysical parameters. Particularly exciting would be thermal conductivity, as that would have applications for geothermal. But we're of the opinion that any attribute that's controlled by mineralogy should be predictable from the hyperspectral, which is also controlled by mineralogy. Whether that plays out or not, we'll see. It's a research project. The GSI has also funded a short call with NUIG, and they're going to be using the hyperspectral to look at some quaternary cave sediments in a karst system to see what they can come up with out of that, and that will be quite interesting. And GSI recently founded is a strong word, but we hosted the first international working group on hyperspectral core scanning in November, and that was very well attended by industry, academia, and Geological Survey. And there are future meetings in planning. The Swedish Geological Survey, the Norwegian Geological Survey, the BGS and GSNI were all present at the meeting, and we kind of had an agreement we would work together to try and develop a network of spectrally active European surveys to get more involved in this working group, because as a geological survey, you have a bit more freedom to do these things than industry and academia, but industry and academia would benefit from being in the same group. So that's what's coming up for the future. I'm personally quite excited by it all. And these are the references I've used throughout this paper. If you have any questions on this work or hyperspectral in data, if you have any criticism of this work, or you have any ideas for collaboration, please contact me. I'd be delighted to hear from anybody. Thank you very much.
Yeah, wow. Thank you very much, Russell. This was a very impressive talk, and the hyperspectral core analysis seems to be a very useful tool. And while you were talking, and you could see it, there were already several comments within the chat, and one I would like to say immediately, which is, would you be happy to share your presentation, because there's quite some interest on that one?
Yes. Also, the case study is lifted from an open access paper that Marcus and I published. I can share the link to that as well if anybody was interested.
Yeah, wonderful. I think I would first go into the audience, which is still rather large. We had up to 90 participants now, and it's still 80. So this shows how interested the public, the geological community is in what you have done. A lot of positive feedback, great work. You will see this in the chat. But I would like first to ask to the audience, now you can ask immediately and personally your questions to Russell before we go into the questions asked in the chat. So please. I can't see a hand, but if I see one, I will hopefully spot it quickly. As I can see, Russell, you have overwhelmed everybody because this was really incredibly full of information. And
yeah, I was too clear. I'm sure that's the case.
So let's go to Kati from Finland, from the Geological Survey from Finland. Kati, are you still in?
Yes, here I am. Actually,
yes.
Hi.
Yes. Yeah. Would you like?
I thanks for the presentation, Russell.
Yeah. Sorry, can you say that again?
I was saying thank you for the presentation.
Okay, thank you for coming.
I guess I can now say my questions in person.
Yes, please.
So my questions were related to the availability of your hyperspectral data. So do you have it somewhere online already? Because I would be very, very keen to see.
Unfortunately,
have a look at your data if you have it available. Yeah.
Unfortunately, we're a bit behind Sweden because they can just email you a link and you can download the data. We haven't solved distribution issues yet. If you're looking for one or two holes, I have a file sharing system that I can send them to you one by one. The other way we've distributed the data is people have posted us a hard drive and we've uploaded the data and posted it back. For the time being, these are the main two methods of distribution, which is not ideal, I have to say. Does that answer your question?
Well, okay, thank you. Thank you very much. I guess I don't know if there's an interest group that maybe like a mailing list or something that I could join and I could have more information when you have something available.
Well, if you have my email, you can email.
Yeah. I will send you an email. Maybe that's the best thing to do. Thank you.
Yeah, for the moment, unfortunately, that is the best way to do it. Okay, were there any other questions in there? Yeah, that was the link to the drill group. Oh yes, so
yes. Sorry, I tried to raise up the hands, and I don't
sorry, I didn't see it. Please ask it.
Okay, thank you. It's a really great presentation, and see all how is going on different geological survey. Unfortunately, on the French side, we cannot reach the meeting at the when you regroup everybody, and obviously we are super interested to participate a kind of a big consortium, because we are as well working on hyperspectral data for coring too. For course, just two maybe questions. One is concerning more availability of the data. How do you process, or how is your mind to show hyperspectral data that you have, and do you show like a kind of generic maps before to provide and see if there is interesting thing inside the cores or not? This is a kind of first question. And the second is, you show a case study that you are looking for specific peaks, you know, that you are looking first for carbonates. What's your strategy where like you don't know what you are looking for, and you kind of find kind of cluster of peaks or things like that and apply specific library? Is a question that we are working on to at the moment. Again, thanks a lot for the presentation.
So the first question is, yes. So our scanner was provided to us by TerraCore. So all of the data that we've scanned is available in IntelliCore, and it's public outside of the login that you need to view it that way. But all that's available there is the RGB and some of their off-the-shelf techniques that they run on everything. So you'll get the mineral map, which is produced from their library, but it's not targeted as just everything in the library against everything. So you do get some strange results, and you get a lot of unclassified minerals. So regarding when I'm looking in carbonates, and then there's something that I'm not expecting in the carbonate, that's something I haven't thought about really, because for this case study, it's a question of scale. If you have like 5 centimeters of a tuff in there, it's not really gonna hamper the interpretation. But it's something that needs to be thought about. And I do have a project in the back of my mind. I was discussing with one of my colleagues. We're going to try and identify bentonites and things that are in tuffs so that we can pull them out. But yeah, it's a good question and interesting. And I guess it depends on how the project that you're doing this for is defined. You know, if you're looking to try and find specific horizons, or if you're looking to see what's there, the approach would be very different. And yeah, if you send me an email as well, I'll get you on the mailing list for the working group, because yeah, we tried our best to reach everybody.
Yeah, but it would be cool. And as we have a kind of project which is like a strategy, we are looking super in details on the hyperspectral data, like just on 1 meter core. So it's interesting to see the other scale, and super interested. So yeah, I will send you an email with my colleagues. So thanks a lot.
Can you include your project as well? Because I'd be interested in looking at the scale I'm not using. You know?
Yeah, but you can look as really, and it will be an advertisement for the project that we have. Is a European project named SOLSA, SOLSA DMAP. I will put the link in on the website, and you will have a look on the project.
Thank you.
Thank you, Aurelian. I have seen in the chat that Stefan Luch from SGU is also congratulating you for this presentation. And he has a question. Stefan, are you still in? And would you like to ask your question and give your comment personally?
Yeah, I'm still in, but I'm not sure if you can hear me.
Yes.
Yeah.
Okay. Okay. Great. Well, thanks, Russell, for this very nice presentation. And
now we can't hear you.
Now we can't hear. Stefan, perhaps I read the question and Russell can answer it. So he says, great work and presentation. I'm just wondering how you organize your spectral logs. I mean, are they Excel friendly? So can the result easily be important in 3D model tools, for example? That's the question from Stefan. Sorry, Stefan, we couldn't hear you. You were just gone. Now you're back.
That's okay. Oh, I'm back. Okay.
Okay, so yeah, that's an excellent question. So what we're actually looking at here, these aren't spectral logs. What these are is each core box concatenated in order. So you're actually looking at the whole core run, 1.5 meters long. And the reason I do that is to leverage the images. We started working on another way of doing it, which is to take the average value across the core at each pixel, which you can then assign a depth to, and then you can do a lot of smoothing. Let me see. Let me just try and find the poster. And this is something that we're still working on. But you can produce logs, which would be the average. But it's very I can't find it. It's very early phase. But yes, getting them into 3D models is something that I haven't got the code perfected for. But there are commercial softwares that can do it in a variety of different ways to enable that.
Okay. Good, thanks.
Right. I can't see any other hands. Is there anybody else who would like to ask a question or comment on this very full of information talk from Brussels?
I have a quick question, if I may.
Yes, please.
I'm wondering on the slide that was one of your slides is really interesting me. It was Irish Mineral Museum collection of actual minerals that you're going to be scanning. Yeah, that's it. Do you have any SWIR or MWIR cubes that you could share yet from that library of pure minerals?
Yeah, we've so far scanned two pallets worth, but they're weird minerals. Like they're not giving us they're giving us the minerals in the order that they come out of the cupboard. So we've got like argentite and things like that. But I can certainly share them what we have so far. Yes.
Oh, that would be fantastic.
Yeah,
is there? There's no. Yeah, there's.
For example, we haven't got to the quartz, the calcite, the feldspars, the clays. It's all like strange minerals so far. But we're going to scan.
Thank you, Russell.
No problem. I saw another question in the chat there.
Yes. So please, Annie Root, would you like to ask your question personally, if you're still in?
Hello, can you hear me?
Yes.
Hi, Russell. I'm a PhD research scholar from India. I just wanted to know which software are you using for applying the corrections and masking? And one more question you mentioned. Okay, please answer this. I'll ask the second question later.
So everything is done in Python. So yeah, everything's done in Python.
Can this be done on NV software?
Yes, Envy can do it, but I don't have an Envy license, so I can't help you with how. But we'll be releasing the Python scripts for the full pre-processing pipeline. This is for the GSI's pre-processing pipeline. But the highlight library, if you check it out on GitHub, they have a number of examples of how to work through the hyperspectral data using their library, and that will cover correction and so on. And actually, the highlight library does the correction for you. You just feed it the folder, and it will produce a reflectance cube.
Okay, and would it be better to use instead you are using a hyperspectral imaging camera, but instead of that, if you use a spectroradiometer to like document the whole core log, so is it better than, or would it be a more time-consuming process compared to this?
So first of all, I don't know if that will be better. As I mentioned right at the very beginning, I'm not a hyperspectral expert. And secondly, the reason we use the aluminium and the white reference method for the correction is because that's what we have.
All right.
When we ordered the scanner, and that's what it came with. So we use it, and we be able to extract some data. As I said, like I'm not a hyperspectral expert, so this isn't perhaps the most optimized path line, and our acquisition's perhaps not the most pristine way of doing it. We're working with what we have, and very keen to hear suggestions for improving on it. Definitely.
Right, because we are using for ground truthing, we are using a spectroradiometer to analyze the mineral samples and the rock samples so as to identify the alteration mineral zones in the area. So
using
for that,
you're
we are
using-
using, yeah,
That's for ground truth after you've done the core scanning.
yeah. Okay.
Well, that's very interesting.
Yeah. So, but I'm not, you're using it for the core samples. I'm actually using your satellite imagery for mapping the area. So you're
Yeah.
doing at a core level. I'm actually just observing it in the on the basis of the alteration minerals which are present in the area using a satellite image. But the idea seems to be more useful when it comes to like detailed mapping of a mining site. So it would be helpful for me in the future, in my future research studies.
Yeah. Well, as I said, we used thin sections for ground truthing, but that's not because it was the best method for ground truthing. It's because that's what we had.
All right. And the aluminium you mentioned, Spectralon is the white base which you are taking. Apart from that, you mentioned aluminium. What is that for?
That's the white reference for the medium wave data set.
Oh, okay. All right. So the white is for the visible.
Yeah, the Spectralon we use is the white reference for the visible and the shortwave cameras, and then we use aluminium
Okay.
for the white reference for the medium wave camera.
All right. Thank you.
Anirudh, if you perhaps would like to have more detailed contact with Russell, if you allow, I will put your email address in the chat,
Yeah,
so
no, please do.
others may use it and come back to you. And the last question I see is from Angela, and I don't want to forget her. Wherever she is coming from, Angela, please go ahead, and I will put your email address into the chat, Russell. Okay.
Please do, yeah.
Yeah.
Hello everyone, this is Angela. I'm from the Netherlands, from TNO, and I have a question, a quick one, I hope. Can we use this methodology to identify interval with bitumen and to quantify the bitumen amount?
Yeah, I don't know. It's a good question. Actually, one of the reviewers on our paper suggested we should try and develop a way of quantifying the organics present. But I mean, we haven't got very far in it because basically we're inferring the presence of organics by the absence of something else. So that's quite hard to do. In terms of bitumen itself, I would think that's probably I don't think it's terribly active in the SWR and WR range, but I don't know. You might be able to see bitumen in the very near infrared. I honestly don't know. I don't know. It's not something I've looked into, but if there are papers out there, they may point you in the right direction. And I mean, there are a number of European surveys have very near infrared cameras, and the university in Helmholtz as well. And you're from Denmark, I think. I'm not sure if Denmark has a camera, but it might be something to think about as a potential application. But I'm afraid I don't know.
Thank you.
Angela, I've done some work with the oil sands in Canada, and the SWR band 1710 and 2310 are very strong in the bitumen, and you can quantify them to predict total bitumen content.
Really?
But that is for rock that has 30% porosity. So this rock is very low porosity, the one that Russell has shown. So it might not work as well. Probably a lot more air involved, but it can be done. And there's some good papers out there if you look at Benoit Rivard from the University of Alberta. He's done a lot of work with TBC on oil sands. It could be a good reference for you.
Oh, thank you very much.
Angela, if you want to paste me some core with bitumen, then we can scan it and see what we see.
Oh, that also could be interesting. We don't have it at the moment. It's a project that we are thinking about.
Okay.
We will have to discuss with the client, but thank you.
Oh, if it's for the client, one of the stipulations for us scanning anything is the data will be made public.
Yeah, that's a little tricky because it's a client from the Middle East, so probably there is a lot of confidentiality on the data.
Oh, well, there are plenty of people who take money to scan stuff, just not the Geological Survey of Ireland.
Yeah, okay.
So, thank you. We also have a comment from Finland, from somebody called SA, that Finland would like to join your data archive network, as far as I can read this, Russell. And it is said that the GTK has scanned over 150 kilometers of AHE and 173 meters of LIBS. So perhaps you can get bilaterally into contact. Yeah. I think this is great.
Well, it sounds like they should join our network of spectrally active surveys anyway, or at least definitely if you send me an email, I'll definitely follow up. I'd be interested to hear more about that.
Yes. So we are a bit over time, but the questions and your answers have been so important and so interesting. And I bet you get a lot of mails after this talk. So now I have a lot of thanks for a lot of people. First of all, to everybody attending this really excellent and highly interesting talk by Russell Rogers. Thank you. I would like to thank Russell, of course, for this great talk, which was really enlightening. And I'm sure you will, maybe there will be some new cooperation coming out of this. And then I would like to thank Marina and EuroGeoSurveys for setting this up and doing the introduction. Thank you so much for everyone.
Thank you, Christine, and thank you, Russell. It was really great to have you here.
Yes, and I look forward to seeing you all for our